Okay, so one of the final topics that we're going to be looking at is the idea of a triple integral. And first, all we're going to be doing is we're going to be looking at it in Cartesian coordinates. And then later, what we're going to be doing is we're going to be looking at it in two other coordinate systems. The idea of a triple coordinate is instead of utilizing rectangles, what we do is we utilize cubes to be able to approximate a volume. So, let's say we have a triple Riemann sum, and let's say it's at the point of fx sub ijk, y ijk, z ijk with delta v, and that's just a sample point that's in the cube. And of course what we'd like to do is we'd like to get to an infinite number of those cubes to be able to approximate the volume. We can clearly see that in this diagram that the idea of breaking them up into smaller cubes is prevalent. So we just have some sort of point fx ijk, y ijk, z ijk. And so what we can do from there is just go ahead and compute the triple integral and to represent a volume. Now the good news is that with Fubini's theorem, if you have a rectangular box, okay, so that means that we just have some sort of Cartesian region, then we can go ahead and we can compute that volume by saying bounds with respect to x, bounds with respect to y, bounds with respect to z. So, in our first few examples of triple integrals, all we're going to be doing is just evaluating triple integrals and then perhaps finding a specific volume. So, let's say we have a triple integral. We don't know the bounds yet, where E is the region bound under the plane z equals 1 plus x plus y above the xy plane, and we're bounded by the curves y equals square root of x, y equals 0, and x equals 1. So, two things going on here. The xy plane, okay, the equation for the xy plane is z equals 0. So we have to be cognizant of that, because what we're doing is we're trying to find everything above the xy plane. So that means that in this case, z is going to go from 0 to 1 plus x plus y. If we were to go ahead and draw, now this is in the xy plane. So we know that y equals root x looks like this, x equals 1 looks like this. Okay, so this is y equals root x. And then what we can do is we can go ahead and write this as a type 1 region where we're going up and down. We could very easily see that this is the point 1, 1. All right, so if x equals 1, we just substitute back into there. And then if y equals 0, clearly x has to equal 0 as well. So I don't think we need to go through and verify that algebraically. I think you guys can all see that using inspection. So here's going to be our triple integral for this particular problem, and then we're going to have to evaluate. So we have integral. Now we're going to go dz, dy, dx. So let's do x first. Since it's going to be a type 1 region, that means that y is going to range from 0 to root x, and x is going to range from 0 to 1. So now we can go ahead and set it up. So we have 0 to 1. We have 0 to root x, and then we have 0 to 1 plus x plus y. All right, because that's our given plane. The integrand is 6x, and then we have dz, dy, dx. And at this point, now we're just going to go ahead and evaluate that triple integral by working from inner to outer. All right. Notice that we can't break this up into 3 separate integrals. Reason being is because 2 of the bounds are variable bounds. So let's just start with z. Antiderivative of 6x with respect to z is going to be 6xz. So now we're going to get integral from 0 to 1, 0 to root x, 6xz, where z is going to range from 0 to 1 plus x plus y. Now we still have dy dx. If we substitute 0, since it's a polynomial, 0 is not going to contribute anything to the sum. So now we can rewrite this as 0 to 1, 0 to root x, 6x, 1 plus x plus y, dy dx. And now we just have a double integral. We can distribute the x, or the 6x. We can factor the 6x out if we want to. And that's going to become 6x plus 6x squared plus 6xy dy dx. We're going to go ahead now and integrate with respect to y. So, oh, excuse me, all those 6's are non-existent because the 6 was factored on the outside. So that 6 is gone, this 6 is gone, and this 6 is gone. So sorry about that. We're now going to integrate everything with respect to y. So 6 integrals from 0 to 1. With respect to y, we get xy, x square y, plus 1/2 xy squared. Now y is going to range from 0 to the square root of x, and we still have dx in there. All right, so we're getting closer. Fortunately, the bounds for x are 0 to 1, so the square root's not going to play too much of an ugly role with this. 6 integrals, 0 to 1. Now again, 0 is inconsequential because it's going to be because we have a polynomial. So we're going to write this now as x root x plus x squared root x plus 1/2 x root x squared dx. Or, if we were to go ahead and remember that the square root of x is the same thing as x to the 1/2, we could just combine the exponents, and we're going to get 6 integrals from 0 to 1 of x to the 3/2 plus x to the 5/2 plus 1/2 x squared. All right, so square root of x squared is just going to be x. X times x is x squared dx. All right, getting closer. Now we have 6, and we're going to take the antiderivative. So this is going to be x to the 5/2 over 5/2 plus x to the 7/2 over 7/2 plus 1/2 x cubed over 3 from 0 to 1. Fortunately, again, even though we don't have polynomial expressions, we do have expressions to where 0 is not going to contribute to the sum. So the 0 doesn't matter in this case. So we're going to end up with 6 times 2/5 of 1 to the 5/2 plus 2/7 times 1 to the 7/2 plus 1/6 of 1 cubed. And I'm just going to shove that into my calculator so we can finish this off. And just give me one moment while I do that. 6 times 2/5 plus 2/7 plus 1/6. So ultimately I get 24.4 or 1/22/5. So hopefully this has been a pretty good introduction for you to be able to see how to go through and evaluate a triple integral.